Forget the usual preamble today because we are tackling a topic so genuinely mind-bending, it literally feels like pure science fiction. If you were trying to invent a subject with an impossible-to-resist hook, you'd probably come up with something like cosmic strings. But we didn't invent them. Astrophysicists think they might actually be out there right now. We're skipping the fluff in today's explainer because we are diving straight into the absolute limits of known physics. I mean, seriously, what if the universe is literally cracked? And I don't mean figuratively or metaphorically, I mean structurally flawed. It sounds like a glitch in a simulation, right? But posing this question instantly challenges our most basic perception of reality, and it is a very active, very real debate in modern astrophysics. Okay, let's just dive right into it. The punchline here is cosmic strings. These are hypothesized as literal, physical, one-dimensional flaws in the fabric of reality itself. We're exploring the staggering possibility that space isn't perfectly smooth, but actually has microscopic fault lines running right through the middle of it. So, Section 1, Cracks in our universe. Let's talk about a pretty wild prediction from 1976. This whole crazy narrative doesn't actually start with a telescope spotting something weird in the night sky. No, it begins on the chalkboard of theoretical physicist Thomas Kibble. He predicted the existence of what he called topological defects. And this illustrates the core concept brilliantly. They are made of absolutely nothing. Think about a wrinkle in your favorite shirt. The wrinkle isn't some foreign material, right? It's not a thread or a stain. It's just your shirt in an uncomfortable, flawed arrangement. A cosmic string is exactly like that, a wrinkle made of nothing but space-time itself. Which brings us to Section 2, how space itself froze, and the massive phase transition that caused it. You're probably thinking, how on earth does reality actually get a crack in it in the first place? Well, to answer that, we have to travel all the way back to the incredibly chaotic fractions of a second immediately following the Big Bang. Conditions back then were so extreme that the fundamental forces of nature, things like gravity and electromagnetism, were mashed together into one unified superforce. But as the universe rapidly expanded and cooled, these forces violently fractured and split apart. This abrupt change is what we call a phase transition, and it literally caused space itself to shudder and quake. To put this into perspective, think about an everyday phase transition, like water freezing into an ice cube. If you look closely at that ice, it's rarely ever perfectly clear. You see imperfections, right? Little white cracks, bubbles, fault lines trapped inside where the water molecules just didn't align perfectly. Just as water freezing imperfectly leaves behind visual cracks, physicists believe the universe rapidly cooling and transitioning left behind its own structural imperfections. Cosmic strings.
All right, Section 3, the physics of a string. And honestly, this is where things get truly extreme.
Now, what's really interesting here is the sheer absurd contrast in these properties. It's what makes them arguably the strangest inhabitants of our cosmos. A cosmic string would have the microscopic width of a single subatomic proton, yet it could extend for hundreds of millions of light years. It could potentially span the entire observable universe. And because they're made of nothing, they exert zero gravitational pull of their own. But they warp space-time so severely that if you looked at distant starlight passing by one, the string would literally split the light, giving you a duplicate mirror image of the star. And because they distort space-time so intensely, they pack an unfathomable amount of energy. To give you an idea, just 1 single kilometer of this microscopic string contains the equivalent mass of our entire planet. Because of this extreme density and their razor-thin profile, if a cosmic string happened to whip through our solar system, it would slice cleanly through the Earth without even slowing down. Oh, and make no mistake, they aren't just statically sitting out there in the void. Cosmic strings would whip, wriggle, and vibrate violently at the speed of light. And as they thrash around in space, they inevitably cross over each other and form closed loops. Now, when a loop forms, it's totally doomed. It vibrates itself into oblivion, rapidly decaying and releasing massive amounts of energy in the form of gravitational waves. Moving right along to Section 4, hearing the cosmic hum. Let's look at 15 years of incredible data. For decades, this whole concept was kind of just a mathematical ghost story. But recently, it's turned into a massive, modern-day cosmic detective mystery. A collaboration known as Nanograv spent 15 years analyzing data from pulsars, which are essentially dead, rapidly spinning stars. By monitoring the unbelievably precise timing of these pulsars, astronomers effectively built a galaxy-sized antenna.
and they actually detected something profound: a low-frequency gravitational rumble, a constant hum that is rhythmically stretching and squeezing the fabric of space-time all around us. So what's actually making that noise? That brings us to Section 5, hunting for the evidence. We're finally connecting these highly theoretical strings to a very real gravitational wave discovery. The leading candidate for this background noise is a huge population of supermassive black hole binaries, basically giant black holes slowly orbiting each other after their host galaxies collided. But sitting right there next to them is the dark horse candidate, cosmic strings. The energy radiating from those decaying loops of string we were just talking about, it would perfectly match the gravitational wave data we are receiving right now. To get a sense of where the science is actually at right now, astrophysicist Dr. Michael Lamb points out, right now we cannot definitively say whether the source of gravitational waves is from supermassive black hole binaries or cosmic strings. Both remain incredibly valid, very real possibilities based entirely on the hard data. Regardless of what the ultimate source turns out to be, this whole thing beautifully reflects the ongoing nature of discovery. Like Dr. Scott Ransom notes, now we know that it's music coming from the gravitational universe. Just the act of hearing the universe in this way opens up a brand new frontier of astrophysics. It's fundamentally changing how we study the cosmos. Which brings us to a close with a final, kind of provocative thought to leave you with. If you bumped into a crack in reality, what would you find? Are we literally on the verge of proving that our universe is fundamentally flawed, bearing the physical scars of its own violent birth? It's a fascinating reminder of the absolute limits of known physics and just how much is left out there to be discovered. I really hope this leaves you eager to learn more. Thanks for joining me for today's explainer of this truly incredible source material.